Hi everyone! Today let's talk about section 3.2, Matrices and Gaussian Elimination. So last session we learned about linear systems. So here let's consider a general linear systems. So here we have a systems of how many equations? So first equation, second equation, so there are actually m equations. Okay, and how many unknown? So the a and the b, they are coefficients. So we have x are the unknown, right? So x1, x2, xn. So here we have n unknown. Okay, so let's introduce some shorthand notations, which is the vector matrix notations. So for the matrix, let's put down all the coefficients into the matrix. Okay, so A11, so the rows corresponds to the equations, the columns corresponds to the unknowns, right? So A11 is here, A12 is here, and then A1n is there. So you can see here we have m rows that corresponds to the equations, and here we have n columns that corresponds to the unknowns. We have n unknowns, and then we have the unknowns. There are x1, x2, xn. So this is the unknown vector, and then the right hand side we have b1 to bn. Okay, so let's see the x. So x vector x1 to xn, this is the vector of unknowns with dimension n by 1. So dimension of a matrix or vector, this is how we define. We use n by n. N is the number of rows, and n is the number of columns. Okay? So this guy, you can see we have n rows. So that's why we have n by 1 column. Okay, so this is a column vector. And b is the known coefficients on the right hand side of the linear systems with the dimension n by 1 because it has m rows and 1 column. Okay, and the matrix A is called a coefficient matrix, and the dimension is m by n because it has m rows and n columns. Then for the system, we can write it as A times X equals to B. So this is a shorthand notation for the original linear system with m equations and n unknown. Okay? So here we have A is known because we know the coefficient values, A1, A11, A12, etc. Okay, and x are the unknown vector because we want to solve the unknown x. Okay, and then b is some known value. Okay, so our goal is to solve for x. So when we adjoin the constant vector b to the coefficient matrix A, we get a m by n plus 1 augmented coefficient matrix. So this is the augmented coefficient matrix. Is actually A, and then we put the vector b there. So this new matrix is an m by n plus 1 dimension matrix. It has one more column than the original matrix A. Okay, so let's look at example 1. The augmented coefficients of the system is what? So let's look at the first equations. So the coefficients are 2, 3, minus 7, and 4. Well, we actually need more. So we actually need more. And 6 here. Okay. The next second equations, because we don't have x1, so the coefficient of x1 is 0, x2 we have 1, x3 we have 3, x4 we have -5, and the right hand side is 0. Okay, so sometimes we put a dashed line here to separate. The left side is the matrix, coefficient matrix. The right side is the right hand side of the linear systems. Okay, and then the third equations we have -1 x1 plus 2 x2, and then we don't have x3, so that's why 0 x3, and -9 x4 equals to 17. Okay, so this is the augmented coefficient matrix. Do you get the same answer? So remember, when we try the problems, you can pause the video and work on the problem first. And after you finish, you can continue to play the video and check your answers. And don't forget that you can always control the speed of the video. Alright, next. The process of Gaussian elimination consists of elementary row operations that transform the linear system AX equals to B into an equivalent system A prime X equals to B prime. So A prime and B prime, they are different matrix and vectors, okay? But this new systems, we can back solve to find the X. So I will explain what it means later. But first, what is elementary row operations? So remember last session when we solved the systems of linear equations, we talked about there are 3 operations we can do, then the linear systems still have the same solutions. So we can multiply any single row of A by a non-zero constant. And then we can also interchange 2 rows of A. We can add a constant multiple of one row to another. So these are the 3 elementary row operations we can do. Okay? So notation. When we multiply a row P by C, this is the notation. So we use C times row P. And when we interchange row P and row Q, we use this notation swap row P and row Q. When we add C times row P to row Q, so this is what we do. C times row P add to row Q, and the resulting row will replace row Q, okay? So we will replace row Q with this new row, CR, row P plus row Q, okay? So let me write this down. The resulting row will replace row Q. Okay, so this is example 2. So how do we solve this system by the Gaussian elimination? So first, we want to rewrite this linear systems into the augmented coefficient matrix. So augmented coefficient matrix, we put on the coefficients of x1 is 2, and then 4, -1, and -1. Okay, how about the second row and the third row? So I suggest you to pause the video and then write it down. Okay, are you ready? Okay, so x1, 1x1, 3x2, -1, x3, and -2. Last one, 1, but no x2, 2x3, and 2. So this is the augmented coefficient matrix. Okay, so what we're gonna do, we're gonna do the Gaussian elimination. What is Gaussian elimination? How it works is we want to make the 1 entry 1, and then we want to use it to kill the entries below it. Okay, so how do we make this guy 1? Well, there are many different ways. We can divide it the first row by 2, then we can get 1. But the bad thing is we will get fractions, right? -1 divided by 2, it becomes -1/2. Oh, we don't want to work with fractions. We would try our best to avoid fractions if we can. Do you like to work with fractions or integers? Of course, integers, right? So don't use this way, okay? The second way, we can interchange row 1 and row 2, right? Then we can get the 1 entry 1. We can also interchange row 1 and row 3. Then we can get the 1 entry to be 1. And which way is easier? You can see the coefficients in the entries in row 3 are easier than in row 2. So I would say interchange row 1 and row 3 is easier. Okay, so let's swap row 1 and row 3. Again, there are many different ways to solve a linear systems. Some way, maybe you just take it just take 10 minutes to solve it. Some other way, it might take an hour to solve it. So I would say before you actually working on it, think about which way is easier. Okay, pick the better way. Okay, swap row 1 and row 3. Then we have 1, 0, 2, 2. Second row stay the same. 1, 3, minus 1, minus 2. And then the row 3 becomes the original row 1. So 2, 4, minus 1, minus 1. Okay. Alright. So after we make the 1, entry 1. Okay. So I'm going to use a different color. Okay. So we want to make the 1, entry to be 1. And then next, we want to use it. So use it to queue the below entries. How? Okay, how do we queue this one? Well, we can use this second row subtracts the first row, right? Okay, so let's see. How do we queue this row? And because we want to have the first row stay there, and we want to replace the second row by the new row. So that's why the row operation we should do is we use minus row 1 add to row 2. Why don't we write row 2 minus row 1? So row 2 minus row 1 means you're going to replace row 1 with this resulting new row. So we don't want to replace row 1, we want to replace row 2. That's why we want to put row 2 in the second place. Okay? So minus row 1 plus row 2. Okay, now let's see. We have 1 minus 1 is 0. And then 3 minus 0 is 3. Minus 1 minus 2 is negative 3. Minus 2 minus 2 is minus 4. Is that okay, everyone? We're actually using the second row to subtract the first row, right? So 1 minus 1 is 0. 3 minus 0 is 3. Minus 1 minus 2 is negative 3. Minus 2 minus 2 is negative 4. Okay, but when we put down the row operation, we put minus row 1 add to row 2. Okay. Alright, so this is a new row 2. How about the third row? How do we queue the 2? Well, 2 minus 2 is 2, right? So we use negative 2 times row 1 add to row 3. Okay, minus 2 times row 1 add to row 3. Then this new row is gonna replace the row 3. Okay, so let's see. 2 minus 2 times 1 is 2 minus 2 is 0. 4 minus 2 times 0 is like 4 minus 0 is 4. Minus 1 minus 2 times 2. So minus 1 minus 4 is minus 5. Minus 1 minus 2 times 2. Minus 1 minus 4 is minus 5. Okay. So, yeah, if this is new to you, you might want to use your scratch paper, okay, and practice more. Alright. Let me erase this. Okay, now you can see we already used the 1 entry and queued all the entries below it. Now we're good. What is the next step? Well, the next step is we're gonna make the 2 entry to be 1. How do we make this guy to be 1? Well, we can divide it by 3, but oops, divided by 3, what happened? This guy, we will get a fraction. No. We don't want to work with fractions. Is there any way we can get 1 here? Look at this 4. You have 3 and you have 4. What do you think? How do you get 1? We know 4 minus 3 is 1. Yes. Here we can see 4 minus 3 is 1. So how do we get 4 minus 3? Well, we're using row 3 minus row 2. And we want to replace row 2 with the new resulting row. So that's why row 2 is in the second place. So this is good. Alright. So by the way, when you do your homework or write your answers in the exams or quizzes, please write down everything, show all your work. So this is how you're gonna do it. Every step you're gonna tell me what operation you do, okay? Otherwise you will lose some points. Okay, next. So first row stay the same. Second row, 4 minus 3 is 1, and then minus 5 minus negative 3 is like minus 5 plus 3 is negative 2. And then minus 5 minus negative 4, minus 5 plus 4 is negative 1. Okay, so, and then the last row stay the same. Alright. Okay, what's next? Alright, next we gonna use the 2 entry to queue the entry below it. Okay, so the last step, use this guy to queue the entry below it. Alright, let's see. Okay, how do we do it? Well, first row stay the same. Second row stay the same. Okay, and then okay, we use 1 to queue the 4. How do we do it? We can use minus 4r2 plus r3. Okay, everyone? So we get 0. 4 minus 4 is 0. Minus 5 minus 4 times negative 2. So it's like 8 minus 5, 3. Minus 5 minus 4 times negative 1. So minus 5 plus 4, which is minus 1. Okay. Now, can you see we have a stair shape? With the left lower corners are zeros. This is good. We can stop here. Okay, so here we get stair shape. Okay, which is good. Okay, now we can start to back solve to find the x1, x2, and x3. Okay, remember the first column corresponds to the coefficient of x1. Second column corresponds to the coefficient of x2. The third column corresponds to the coefficient of x3. And the fourth column corresponds to the right-hand side of the of the linear system. Okay, so what does the last row tell us? So last row tell us that 3 times x3 equals minus 1. Okay, don't forget the x3, because without the x3, you're talking about, oh, 3 equals minus 1. This is impossible, right? You get no solution in that. Wow. So here, we have 3 times x3 is minus 1. Then x3 is minus 1/3. So this is the last row. Okay? And then we look at the second row. Second row, we have 1 times x2 minus 2 times x3 equals minus 1. So how do we solve for x2? So x2 is then move the 2x3 to the other side, become positive. And 2x3 is like minus 2/3 minus 1, which is minus 5/3. Right? And then we look at the first row. First row, it tells us 1x1 plus 0 times x2 plus 2 times x3 equals to 2. But then x1 is negative 2x3 plus 2. Well, negative 2 times negative 1/3 is 2/3 plus 2. Well, 2 is like 6 over 3. 2 plus 6 is 8 over 3. So finally, our x1 is 8 over 3. Our x2 is minus 5 over 3. Our x3 is minus 1/3. So we get a unique solution. So this is a solution to the linear systems. Okay? Alright, so couple remark here. First of all, remember the steps. Okay, the first step, we want to make the 1 entry to be 1, and then we want to use it to queue the entries below it. Okay, and so after that, we want to the next step, we want to make the 2 entry to be 1, and then use it to queue the entry below it. And don't touch the first row in the steps. So don't touch the first row. So sometimes students want to create a 1 here, they want to use the first row. Don't touch the first row, because if you touch the first row, you will create non-zero entry in the 2-1 entry. Okay, so don't touch the first row. So once you use the first row to queue the entry below it, don't touch the first row from okay, so here don't touch the first row. Okay, so you just like think about row 2 and row 3. How do you get 1 here? We see 4 minus 3 is 1, so we can use row 2 and row 3. But don't use row 1, because if you use row 1, you might create non-zero entries in the first column. Okay, so be careful, be careful. And you can see at the end, we'll get a stair shape. So the left lower corner, so left lower corner just has zeros. Okay, so zeros. And has 0. Okay, so this is the stair shape, and then we can do back substitution. Why do we say back substitution? Because we look at the last row, and then the second row, and then the first row. So this is the back substitution. Okay, and finally, we get a unique solution in this case. But there could be other possibility, could be no solutions or infinite solution. So we're gonna do more examples in this sessions, then you can see those cases. Alright, so don't forget, when you watch the lecture video, you can always control the speed, and if you have questions, you can ask me in class, or you can print screens and email me. Okay? Alright, so Gaussian elimination. Alright, so we just solved the linear systems with the Gaussian elimination. So what it is, okay? So given a linear systems A, x equals to B, A is m by n matrix. Okay, remember m is the number of rows, n is the number of columns. And x is an m by 1 column vector, and b is an m by 1 column vector. So x and b, they're both column vector. Then we can form the augmented coefficient matrix. Oops, sorry. Sometimes my hand touched the right lower corner. Okay. Alright, so this is the augmented coefficient matrix, right? We use the matrix A adjoined with the vector B. And then we perform elementary row operations. So we put zeros in the columns below. So we want to have the 1 entry to be 1, and then we can use it to queue the entry below it. And then we want to make the 2 entry to be 1, and then use it to queue the entries below it. So this is how we do it. And then after we get a stair shape with all the zeros on the left, and then we can do back substitution. Back substitution means we look at the last row, and then look at the second row, and then look at the first row. So back substitution. Okay, definition. Two matrices are called row equivalents if one can be obtained from the other by a finite sequence of elementary row operations. Okay? So, for example, you can see this matrix and this matrix, they are row equivalents because actually all of these matrices, they are row equivalents. Okay? Because we just perform a sequence of elementary row operations, so all those systems are matrices are equivalent. Okay, next. Theorem. If the augmented coefficient matrices of two linear systems are row equivalent, then the two systems have the same solution sets. And it makes sense. This is how we find the solutions to the linear systems, right? We want to perform a Gaussian elimination so that we can get a stair-shaped matrix. It's easier to do back substitutions to the stair-shaped matrix, then we can solve the solution. Okay. Definitions. So what is this stair-shaped matrix? It has a name. It's called echelon matrix. So a matrix E is called echelon matrix provided it has the following two properties. First property, every row of E that consists entirely of zeros, if there is a row consists of entirely zero, it must lie beneath every row that contains a non-zero element. Okay. Second property, in each row of E that contains a non-zero element, the first non-zero element lies strictly to the right of the first non-zero element in the preceding row, if there is a preceding row. So the first non-zero element in a row is called the leading entry. So what does that mean? Okay, look at this guy. So A22 is the first non-zero element in that row, right? Because this guy is 0, right? So this A22 is the first non-zero element in the second row. So this is a leading entry. And actually, this is leading entry as well. Okay? And then you can see A22 is, it lies strictly to the right of A11. So that's why we get a stair shape. The leading entry lies strictly to the right of the leading entry in the preceding row. So this will give us stair shape. Okay, let me give you more examples. So let's see. 2, 3, 4, 0, 5, 6, 7, 8, 9. Okay, look at this matrix. You can see, oh, the stair is like this. So it is a stair shape. And what are the leading entries? We have 1, 5, and 8. They are the leading entries, right? And you can see there are the lines on the right of the leading entry of the preceding row. So we get stair shape, and the left lower corners are 0. So this is the actual matrix. And we can also have 1, 2, 3, 4, 0, 0, 5, 6, 0, 0, 0, 0. Look at this guy. Do you see the stair shape? It's still stair shaped. So the left lower corner just has zeros. The leading entries, the first row, the leading entry is 1. The second row, the leading entry is 5. And the third row, we don't have a leading entry. And you can see the third row consists of all the 0 amos lines below every row that contains a non-zero element. Okay, so this is also actual matrix. Let's see one more example. So this is also an actual matrix. And here, the first row, we have leading entry 1. The second row, we have leading entry 5. Okay, so this is also actual matrix. So we get stair shape with the left lower corner consists of zeros. So this is actual matrix. Once we get the actual matrix, then we can do back substitution and solve for the unknowns x, y, z, or x1, x2, x3. Okay? Alright, so next we're gonna do more examples to solve the linear system. So example 3, we want to solve the following linear system. Let's see. What is the augmented coefficient matrix? So we have 3. By the way, you can pause the video and then try to work on it. And after you finish, you can play the video and check your answers. Okay? So, are you ready? First row, we have 3, and then 1, and then minus 3, and then the right-hand side is minus 4. Second row, we have 1, 1, 1, 1. Third row, 5, 6, 8, 8. And then, okay, remember, first step, we want to make the 1, 1 entry to be 1. Well, we get a 1 here. So maybe it's easier to interchange row 1 and row 2. Don't divide the first row by 3 because we don't want to work with fractions, right? So we swap row 1 and row 2. Then we get 1, 1, 1, 1. And then 3, 1, minus 3, minus 4, 5, 6, 8, 8. Okay, after we get the one entry to be 1, and then we can use it to kill the entry below it. Okay, so actually, we don't have to make it 1. We want to make it 1 because it's easier for us to kill the entry below it, right? But for example, if your matrix is like 2, 4, 6, well, then you can already use multiple of 2 to get rid of 4 and 6. Then you don't have to make this to be 1. Okay? Alright, let's see. How do we get rid of the 3? We use negative 3 row 1 add to row 2. Okay, 3 minus 3, 0. And then 1 minus 3 is negative 2. Minus 3 times 1. So minus 3 is minus 6. Negative 4 minus 3 times 1. Negative 4 minus 3 is negative 7. Okay? So are you okay with this? Alright. How do we get rid of the 5? We use minus 5 row 1, add to row 3. 5 minus 5, 0. 6 minus 5, 1. 8 minus 5, 3. 8 minus 5, 3. Right? Okay, so this is what we get. And the next step, don't touch row 1 anymore, okay? From now on, don't touch row 1, just touch row 2 and row 3. So how do we make this guy 1? Okay, you can see, we can interchange row 2 and row 3, okay? Don't interchange row 1, because then you will create non-zero entry in the first column, so we don't want to do that. So don't go backwards, okay? This is super important, because I have quite a lot of students make this mistake. So because they touch row 1, then they create non-zero entries here, then they just go back and forth and not getting the echelon form. Alright, so here we're gonna swap row 2 and row 3. Okay, and then so we have 1, 1, 1, 1, 0, 1, 3, 3. And 0 minus 2 minus 6 minus 7. Okay, and in this example, this is easy. We just swap row 2 and row 3. But in some other example, let's see. Okay, if this guy is not 1, if this guy is 5, how do you create 1 there? Well, you think about 5 and negative 2. How do you get 1? Well, you think about, okay, 5 plus 2 times negative 2 is like 5 minus 4 is 1, right? Then what do? You can do 5 row 3 plus 2 row 2. Then this is the row operation you can do. Is that okay, everyone? So we're trying to avoid fractions. So we can use some linear combinations of row 2 and row 3 and try to get 1 in that entry. Okay? Maybe more examples. Okay, if this is 3, this is 5. Okay, so this is, let's say this is row 2 and row 3. If this is 3, this is 5. How do you get 1? Well, you think about 3 and 5, how to get 1? I know 2 times 3 minus 5 is 1, right? Then 2 row 2 minus row 3 will get 1, but I want to replace the row 2 by the new resulting row, so we want to write it as negative row 3 add to 2 row 2. So in this case, it means we're going to replace row 2 by the new resulting row. So this is the correct row operation. Okay, I hope you will do more examples and more exercise with this. Okay. Alright, so let's get that one. And let's see. Okay, so now we can use this one to kill the entry below it. We can use 2 row 2 add to row 3. And 2 minus 2, 0. 2 times 3, 6. Minus 6, 0. 2 times 3, 6. 6 minus 7 is minus 1. Okay. See, now we get a stair shape. So this is the echelon form. And the first column corresponds to the coefficient of x1. Second column corresponds to the coefficient of x2. Third column corresponds to the coefficient of x3. And then the last column corresponds to the right-hand side of the linear systems. Okay, now we can do back substitution. Back substitution, we look at the last row. So the last row, we have 0 times x3 equals minus 1. So it's the same as saying 0 is minus 1. Wow, is this possible? Can 0 be minus 1? So impossible. Or we can say contradictions. What does that mean? So this problem has no solution. Yes. So, right, we just say no solution, and that's the end of this problem. Okay? Yeah, it is possible we do a whole thing and then realize, oops, there's no solution. Okay? So this is example 3. So example 2, we talk about unit solution. Example 3, we talk about no solution. You guess what? In example 4, we should see infinitely many solutions, right? Okay, let's see whether we get that. You can pause the video and try to work on the problem, and then you can continue to play the video. Okay, so look at the first equation. We have 1x1, 0x2, 3x3 is 1, minus 1x1, 2x2, minus 1x3 is 1, 3x1, 1x2, 10x3 is 4. So this is the augmented coefficient matrix. Okay, first thing we want to make the 1 entry 1 good is already 1. So we can use it to kill the entries below it. How do we kill the 2 1 entry? We can use what row operation? Do you know? Row 1 add to row 2. 1 minus 1, 0. 0 plus 2, 2. 3 minus 1, 2. 1 plus 1, 2. Oh, nice. And then, how do we kill the 3 1 entry? We use -3 R1 add to R3. 3 minus 3 is 0. And then 1 minus 3 times 0 is 1. 10 minus 3 times 3 is 10 minus 9, which is 1. 4 minus 3 times 1. 4 minus 3 is 1. Oh, okay. Now, what happened? Okay, can you see we can simplify the second row? We can do 1/2 row 2, 1 0 3 1. Then we get 1 1 1, right? See, we can divide it by 2, and because we have a common factor 2, so we still get integers. Okay, so we can divide, but we just try to avoid fractions. In this case, we still have integers, so we can divide it by 2. Well, do you see now the second row and the third row, they are the same? So how we can use this guy to kill the entry below it? So negative row 2 plus row 3 will give us zeros for the last row because they all cancel out. Okay, now we get a stair shape. So this is the echelon form. First column corresponds to the coefficient of x1. Second column corresponds to the coefficient of x2. Third column corresponds to the coefficient of x3. Last column is the right hand side, right? Okay, now look at this matrix. Look at the first row. Which one is the leading entry? The leading entry is 1, right? Look at the second row. Where's the leading entry? Here, the 2 2 entry is the leading entry. Look at the third row. Do you see a leading entry in the third row? No. Okay. Now, let's look at the columns. The first column, we see it has a leading entry, right? It has a leading entry. Second column, it has a leading entry. But now, do you see the third column? It has no leading entry. Okay, what does that mean by saying this column has no leading entry. It means x3 is free. So x3 is free. Then we have also the last row, because it's all 0, so 0 equals 0, we have infinitely many solutions. And because x3 is free, we can let x3 be the t, the parameter t, okay? And now, what's next? So the second row tells us 1, x2 plus 1, x3 equals 1. So x2 is minus x3 plus 1. x3 is t, so we have minus t plus 1. And then we look at the first row. First row, 1x1 plus 0x2 plus 3x3 is 1. Alright, so x1 is negative 3x3 plus 1. Well, x3 is t, so then we get x1. Now, do you see that? We get x1, x2, x3, they are functions of t, so we get one parameter family. So x1 is negative 3t plus 1. x2 is minus t plus 1. x3 is t. Okay, so t is any real numbers. We get a one parameter family. Okay, this finished the problem. So now we have seen three cases. Unit solution, then we get a point, right? And no solutions, then you just say no solutions. Infinitely many solutions. So infinitely many solutions, we either have one parameter family or two parameter family. So for one parameter family, you usually after you get the echelon form, you usually get the you can see the columns. So which column has no leading entry? Then we know that variable is free. So we just let it be t or s, okay? Then we can solve the other variable in terms of that variable, and then we can get all the variables, they are functions of t, okay? So let's continue in video 2. See you soon!